There we go. So recap from last time, where we are. So the main thing we were talking about at the end last time, if I'm not mistaken, I've been away like many of you, so I almost don't quite remember what we did. I think the last thing we talked about was the construction of the suspension of a type, which is an example. In general, what we're in the middle of doing is discussing the notion of higher inductive types and what you can do by kind of a generalized form of inductive definition or free construction, which in which we can give, one way to view it is equationally constrained inductively defined types. So you could look at it as some kind of general co-limit mechanism. That would be one way to think about it. Or you can think of it more naively in terms of just being given by generators, but the generators consist of, our generators are given at all at arbitrary dimensions, so that you could give the zero cells like you usually do, but you can also give one cells which generate the paths. And then I've made a point of saying that the view of it just as giving generators can be a little misleading, because you're not constructing in the usual sort of inductive definition, you're constructing a set on the which is a least set containing some generators or closed under some operations. For my purposes means the same thing. But there's no structure because it's a set, whereas when working with these infinity groupoids, then there's a lot of implied structure given by the generators, especially at the higher dimensions, and it can be quite subtle or quite a conundrum to understand what that additional structure is. So we were starting out I'm using this is not the standard notation. It's not the notation that's used in the book, because as I mentioned, the notation sigma A, which comes up very often, is overworked in our setting. So I didn't want to use that. But more commonly, it would be probably called that. Okay, so the suspension of A is given at the zero cells by saying there's two designated points, which we think of north and south, are in this type. And then what we have is a meridian, you'll remember, okay, whoops. Meridian, which for every x in A connects north equal to south in, of course, the suspension. And here, that would be that was the formulation we gave, and I drew various pictures. There are different pictures one can draw. One that normally does is think of sort of something like A is looking like this, and then we're adjoining A, and the meridian goes from here to here. So that's one way to think about it. If you think of somehow A living around the periphery here, that would be a way to think about it. So for each, so that would be, then the meridian, this is a continuous path here. I just draw it in a funny way to sort of look good. And another version that Ed pointed out to me that I think is a standard way of visualizing it is if you again think of A like this, then what you're doing is, you could think of yourself as making a cylinder that goes all the way around A, and then with these are their own endpoints. And then what you do is you then identify all of these endpoints. So you sort of bring these around here and pinch them together, and then that would be your north. And then you pinch all these together, and that would be the south. Well, it doesn't make any difference. It's kind of the same thing, but that's apparently that's a pretty common one. The only thing that I would say, about these visualizations is they're visualizations. So really, the definition is that. So that's the main thing. But it's just that in the synthetic approach that we're taking, this kind of axiomatic approach that we're taking here in HOT, is we no longer think of spaces as sets of points, and we no longer, right? So therefore, if we were to think of spaces as sets of points, then there would be, you would kind of imagine there's points all over the place here, and then there's one meridian for each point, and you can kind of feel like it makes a cylinder, or it makes a sheet. But that's fine as far as it goes, but it's one way of interpreting homotopy type theory. It would be into such a setting, but that's not what we're actually doing. So it's a best an analogy, okay, just to say that that's what's going on there. So this is constitutes our higher inductive definition. And now I've forgotten exactly where we got to with this. Most probably we talked about the elimination form or the induction principle, and what this would look like this is if you have some family of types or a predicate, let's call it B of x, okay, indexed over the suspension, then how do I want to be able to say something in general about the suspension of A and say something is true about it, about an arbitrary element of the suspension. And the thing we discuss, as ever, you always have to keep in mind, in homotopy type theory, this is always representing I'll just write it off to the side here. This is always representing a functorial dependency, you might say, or a functorial mapping, okay, that goes from the suspension of A to suspension to the target, whatever that is. Okay, is something wrong? Oh, got the email. Oh, thanks. Did you go scavenge these up or somewhere? Oh, those would be good. Thank you. Okay, good. Oh, these are great, actually. So I'm happy with that. Thank you. Okay, I'll put that there and leave it for a minute. So the point being is you have to do something with the zero cells, clearly. So you would like to say B is true of N, and you have a proof of that. And you'd like to say that B is true of S, and you have a proof of that. So that's the usual kind of naive set theoretic interpretation of type theory, where we do these things kind of pointwise because there's no notion of any kind of cohesion or relatedness between the elements, and so there's nothing else to say. But here we have to worry about that we preserve, okay, the possibility that there are paths in here, okay. And how do we say that? Well, we can say that it's a suspension of A, but the general idea is going to be that N and S, I'm just reminding you here, should be sort of equal, okay? And what does it mean for them to be equal? Well, let me leave a little more room here. So we're going to have a term M witnessing that fact. So first of all, we're in a proof-relevant environment, so we always have that. So we're going to have a term witnessing their equality as you go along any meridian. So there's a meridian for every x and A, so that's the purpose of that, what that is doing. And then this would be z dot B up here. Okay, so that's the idea. And then just to remind you, in case you've checked out for the last few days like I have, then this clause is saying if I transport, okay, with respect to that family or that predicate z dot B, if I transport along the meridian corresponding to x, then n, when transported along the meridian, had better be equal to S, okay? And so that's the definition. But the path over construct, in some sense, makes it more, it's easier. You don't have, when I read this, I decode it and say, oh, I see, it's path over this. So I prefer to think of it like that, even though in our setup anyway, this is not a primitive notion, it's derived from this. Okay, so that was the setup for the induction principle, and I've forgotten again whether we had gotten this far, but the one basic fact is that one use of the suspensions is to build the higher spheres by iterated suspension. So it turns out we can say that this is equivalent to S1. Okay, that's the idea. Where you'll recall S1 was defined, let me sort of shove it in here somewhere. S1 was defined inductively by having a single base point as its zero cell and a single loop which says that the base point is equal in S1 to the base point. Okay, so we're looking at at that structure, so that's what we mean by S1. So there's something to be said here about what we do, okay? So I'll just briefly sketch the proof of this fact. So F is, I'll define a mapping from sus2 to S1, and then I'll show it has a, that it has a quasi-inverse. So the way I'll do this is by defining this by recursion on susp2, which can be thought of as the degenerate case of this, where the dependency where B is constant in X. So we have to just give two elements of B, and then we have to give a proof since that they're equal over the meridian, but that you'll see how that works out. So what we have to do here is we say, I define it like this. We send n, we have to worry about the zero cells, so we send n to base, and we send s to base. In a sense, the way we've defined it, we don't really have a lot of choices here. You know, there's not much we can do. We have to send the zero cells somewhere, and the only one we specify that we know about is base. So it's not like we had any choice here. And the same thing happens with the meridians. So we have two meridians, one corresponding. This is the Boolean, so I'll write true for 1 plus 1, and we've got to send the meridian somewhere. So what do? Well, it turns out we're going to send that to the loop. There's two possibilities. There's two possibilities, and I'm pretty sure you can do this any way you feel like, but I think this is the way I did it in my notes here, so we'll see. So we send that to reflexivity, which is, of course, reflexivity at the base point. So the point is there are two, if we have the base point here, there are two loops available. The reflexivity, which I always draw small, and the loop. Okay, and so if I have two different paths that I know about in the inductively defined suspension, then I send them like that. Okay, so I have to do that. So then I'm going to give the quasi-inverse, so we'll give G. So I'll claim that data gives us a map. You have to write it down. It's a case analysis, and what this is really going to mean is that when I do the app of F to such a path, it will be this path, loop, and so on. So that this is like in scare quotes. Okay, you're supposed to now figure out what I really mean when I write that down, and hopefully I won't make mistakes when I do that. But I don't think I did this time. So I now have G that I'll define. Okay, so S1 to susp A. Okay, and again, I'm going to give this in scare quotes. What do? We have to do something with the zero cells, and there's only one of those that we know about, so we'll send base somewhere. And where are we going to send base? And I think this is just arbitrary. I send it to n. Things have to fit together, but I send it to n. That's how we do this. And then the loop. So the problem is, where do I send the loop? Well, it's going to have to go to a loop in the suspension, and so the only loops you could possibly think of in the suspension involve going some version of a round trip here. Okay, so you can go this way and that way, or all the different ways you can think of it. That's the only chance we have. So what I did here, let me stick with what I did. There's definitely an element of arbitrariness to some of this. So I did this. So I think what I do is I was thinking of this guy in the case that I'm talking about with over there. This guy is the meridian of true. I'm pretty sure that's the way I depicted it, so that if I draw another picture, I hope I'll be consistent with that, and I'll think of that as the meridian of false, because there's two meridians over the Booleans that are going on here. Good, and we do that. Okay, so those are the quasi-inverses. So what we need is an alpha, which says for every x in the suspension of 2, that's what we're working with here, is the suspension of 2. Of course, I want to show you that g of f of x is equal to x. Okay, so we do that. So what do we do here? Well, we're going to do an induction, okay, on x that is given by the induction principle that we send over here. So what are my possibilities? So I wrote it like this. So one to think of is x happens to be north. Then what do? Is I send it to I'm gonna send this to REFL of n, which is a proof that n is equal to n in susp of 2. Let me not write that every time. Okay, so I have to prove that this is that. And when I have x is s, I want to at least get something which is type correct. So if you plug in REFL of n, of course it has that type. But if you look at what g of f of x is doing, n gets sent to base, gets sent to n. So that at least makes some sense. Okay, and then here, I need something that goes from n equals s, okay? Because we're in this thing, we send s to base back to n again. Okay, so that's what we're going to do. So we have n equals s here. We start with s, and then we go from n to base to s. Okay, did I do that right? Okay, and what I have written down here is meridian of false. South to north I want, don't I? Am I correct?
No, because x is s. Right?
X is s. So, oh no, yeah, so the way I wrote it, if I'd written it the other way, it would be that. So this has to be, it looks like I have meridian of false. I don't have an inverse here. What I have here is n equals s.
Yeah.
Okay, is that the right thing? Yep.
Yeah.
Okay, so then what I do is for each meridian y, where y is in 2, remember, okay, I have to do something. So what I'm going to need is something which I didn't name here in my notes, which tells me that REFL of n is equal over the meridian of y, okay, in the path, and then it's that guy up there. So z, let's call it, just to avoid confusing variable names, if there's a chance. So we look at that as our family of type, and I want that guy to be equal to the meridian of f. Okay, that's the thing I need there. Okay, if I did everything right, that's what I need. So the answer you give in each case, they must be equal, modulo the fact that they go around the loop, or go along the meridian y. So there are sort of two cases here. Okay, so what are we really saying here? Right, we're saying two things. We're saying, well, if you work out what that must mean, particularly like this notation, remember, this notation that I used here to help, make the ideas clear is all in scare quotes, because here and here, we're really talking about app of something or other having some equation hold true, and app of something or other having some equation hold true, right? So you have to remember that. What?
Well, I think this term is named beta instead of alpha in the previous.
You think something is what?
Oh, I think beta instead of alpha.
Beta instead of alpha. Oh, I mean because the conventions I usually used or something?
Right.
Yeah, but don't make me change my letters, even if I chose the wrong letter. Okay. It may be that my conventions end up being different from the one that are in the book, if that's what you're worried about. Okay, because it can't possibly matter what I call that. And if you make me change it, I'm going to screw it up even more than normal. So, all right. So let's leave it, call it alpha, okay? Maybe you're right. Maybe in the book it's called something else. Okay, so the point I was trying to remind you was that these really ought to be written out as app of the F has some behavior, app of the G has some behavior. So here I'll make that explicit, okay? So I will say, so what we have is app G of app F of, see where I'm going? Oh yes. If you look at what has to be done here, that's meridian of true, inverse, and you also have to look at the action, what it means to, what is a path in the identity type. So I'm using that fact here as well. So it's given by pre and post composition, but inverse on this side, because everything in the nice thing about the infinity groupoids is everything is covariant, because we can always shove in the inverses in contravariant positions. So that's what we do. Okay, so we put that in, and then that has to be meridian of t. This dot this dot this has to be equal to the meridian of f of false. That's one requirement. And then the other requirement is, of course, going to look a little similar, and it's going to say app of G, app of F, and it says meridian of false has to have that behavior, because you see there are two meridians here. So because Y ranges over 2, and that has no other structure, so this will look like that. And this will be, oops, not REFL here, but what did I send it to? No, here it's REFL. Yeah, it's in the other case that it's not. Okay, so REFL N, and then this is meridian of false, if I transcribe properly. And then this is supposed to be the meridian of false. And then we can just work through it quickly. We can scratch out quickly what's going on. Okay, so that's what we need, right? Since this is true, has to be true over 2, I have 2 cases to consider. Okay, so obviously this cancels out because the concatenation respects that guy. Okay, so we have to look at that. So that's the first thing. Okay, we'll leave that alone for the time being. So if we look further down here, so what we get is, what is that guy equal to? Well, we just have to figure out what does app F of meridian of true do. That's the app I was telling you before. So that is a loop. So that says app G of loop dot the meridian of F is the meridian of F. All right, so that's what we did there. And then the app G part was specified here in that notation, so that ended up being meridian of true dot meridian of false inverse, lo and behold, and that's meridian of false. And of course, those last 2 things cancel, and we get meridian of true, and I hope that's what I was shooting for. It wasn't. What did I do wrong? Oh, wait a minute. I made a mistake here. Hold it. I left out my inverse. So this is inverse, and this is, I did the app G of loop correctly, so hold on a second. This has to be inverse, right? I carried the inverse down and I forgot to do it. Okay, so this is inverse, time that. Okay, good. So then it's meridian true times meridian false inverse. That I did correctly, but I forgot to put the inverse here. Ah, good. Okay, so now, instead of jumping, the other case works like that. Okay, so now the inverse is going to do these things, right? So I'm going to get meridian false inverse inverse, just to be blatant about it, times meridian of true times meridian of false, meridian of true inverse. Suddenly everything looks wrong to me. Somehow this should have been meridian of true all the way along. That's why I got confused as well. Yeah, okay. All right. I should know better than to try to do this, okay, at the board. Okay, so yes, it's what I have in my notes. Okay, so I carried down incorrectly. I made 2 mistakes. I forgot to put the inverse there, and I forgot to put I carried it down like that. Okay, so now I think we're cooking with gas, I hope. So we do this, and now this is times meridian of true. And now the thing that I wanted to comes out, those cancel, and then I get meridian of false, right? Okay, so that works like that. And then step 2 has so that's done, and step 2 looks the same. Okay, basically it actually it's basically the same. Okay, and then the last thing is you have to define a beta, which I won't do everything here, but it's going to say pi x in S1, right? Because we're going to go the other way, so we're going to look at what F does to G of X. So G sends us back to the suspension, then we go back over, and I want that to be equal to X. Okay, now I'm out of chalk. Okay, so I want that to be equal to X. Oh. This is a tough one. It's huh? Oh, you know what's going on? Maybe. there we go. Excuse me for a moment, but it's got quite a good coating here. So I'll try to get that working. Okay, so we have that. So what do I want to do here? So I have to do, obviously I'm going to do this by epsilon induction, right? That's the thing I want to do. So when x is equal to base, S1 induction, which is what am I going to do is when x is equal to base, I have two cases, and then I have to worry about when x is the loop. This is really being preserved. Okay, so when f is the base, well, we can witness this by saying that REFL of base is in fact a proof now of the right thing. If you look at what f of g of base is, that should be equal to base. And of course it is, because if I do g, and I send base to n, and n goes back to base, so I have to be REFL of base, so we're good with that. And then I have to show that it survives the loop, right? So I have to say that we're using the apps here to make explicit, so we have this. So whatever that is, inverse, and remind me to carry the inverse down so I don't make the same mistake again. Okay, so this is base, if I base, and then the loop. Oh, well, sorry. You can read that. It says loop here, and I need to show that this is equal to REFL. If you work it out, this has to be equal to REFL of base. Okay, so we work this out. So this guy is AppF, and then what does G do to the loop? Well, it goes to the loop in the suspension, which I define somewhat arbitrarily as meridian of T times a meridian of false inverse, did I not? Is that the one I did? There are several loops I made. Yeah, that's what I did. And now that whole thing is inverse. Okay, so then I don't mess up. Okay, and then base, and then loop at the end here. Okay, so now what does AppF do with this guy? Well, I need functoriality and stuff, and I have to work it out. So what will end up being is this will be loop inverse, okay, backward, times the REFL of base times the loop. That's what happens here, which ends up being REFL, which is what it has to be. Okay, and that's essentially the argument. Okay, because we have to show alpha and beta. Yeah, I think that's actually the whole of the argument. I'm pretty sure. Okay, so that's it. Okay. So I think so what I was saying, I think at the end last time was, and I want to say something else of a similar flavor in a second, is from a classical sort of textbook point of view, you would expect this to be true. In fact, you could even, a lot of times you could even just define S1 to be the suspension of two. But anyway, here we have two inductive definitions to illustrate this situation, and so we would expect that, given that we define the two things independently of one another, you would expect that they actually are doing the right thing. So the picture is that if I pick, remember it's the one we started with, here are my 2 points, true and false, right? That is in 2, and I pick a meridian from north to south that goes through true, you could say, or is indexed by true, okay? And I pick a meridian from north to south that's indexed by false, or goes through false, then the claim is that that is that. And it is. So that's all that is being said here, but I'm just, and it's such a low dimension, and with the picture it's obvious, but I wanted to go through the argument. Okay, so there's that. So there are other characteristics that one would expect of suspensions, which are actually useful for talking about higher dimensional spheres and higher n types for higher n, which is, in some sense, this is one base case of a more general thing, but it basically tells you, the way I like to think about it is, it's a way of telling you why the spheres. I mean, when I make these motivational remarks, you just have to say that this is a thing that I like. What? Go ahead.
Yeah, I just have a quick question. So in lines 1 and 2 of the 22nd list, there's a missing right parenthesis. Is that right before the inverse?
Okay, good. There may be a missing right paren. Whoever's taking notes could make sure that I don't forget to carry down your inverses and then get the parens right. I forgot to carry down the inverses and then got confused. Okay, so the way I like to think about this is one way of saying, why are the spheres of interest? Well, you could say the spheres are obviously of interest. Well, okay, yeah. But there's a way of saying why the spheres are of interest. So recall that we had this thing that said that the interval was of interest, especially in the synthetic homotopy approach we're doing now. The interval is of interest because indeed it characterizes the total path space that maps from the interval into the type correspond to the total path space of the type, or what I think sometimes that's called the free path space of the type. That is the sum of all the endpoints, all the paths between all the endpoints, okay? So we did that last time. So here there's a similar kind of thing that goes on here, and it requires me to do it. I have to introduce the idea of a pointed type, and you'll notice something comes up here, and I'm going to use some, I think, non-standard notation because the same issue comes up in denotational semantics. So I'll take some inspiration from that. So we have the notion of a pointed type, and there's never, as far as I know, there's no good, nice, convenient notation for pointed types. You always have to have some conventions, but the idea is that it's a type together with a base point, so that this is an element of A. So you're designating a point. So the point that you want to say a pointed type is a type that comes with a designated base point. Now it gets awfully tedious to write it out as pairs all the time, so we don't do that. But we're gonna, so that you'll have to, I'll just say for pointed types, and you're supposed to know that when I write A0 that I mean the base point of A. So I don't know any nice notation to avoid that. You just have to do that. And the thing I want to point out straight away is, as examples of pointed types, or that can be considered as pointed types, would be the loop space. So remember, we define the loop space of A, but usually it's the loop space of A at a base point, okay, is defined. It's just what it means is the loop space of A at the base point. In other words, in the synthetic homotopy theory, the loop space is an abstract notion. So rather than write that notation, we typically write this notation. It says it's the type of all the proofs that A0 is equal to it. The base point is equal to itself, okay? So that's called the loop space. That's one of the nicest notational conventions there is, I think. It just works out so beautifully that omega looks good there. So you always have omega there. So it refers to the loop space, the proofs of self-identity. And the point is that this is pointed, okay, and it's pointed by in the reflexivity there. We'll take that as our designated base point, okay. And another example would be if I take the suspension of A. Okay, then regardless of what A is, okay, it's also pointed, and here it's an arbitrary thing, but I'll just say that north is the base point of suspension, okay? And of course, I could just as well have chosen south, and then everything will have to be changed accordingly, and then but let me not do that. Okay, we can do that. And now the thing is, we can talk about, okay, don't mind me now. So at this point, we'll talk about strict maps. Okay, so in denotational semantics, these are strict maps, but these are really known as pointed maps, or maps in the category of pointed spaces or things like that. Okay, but in denotational semantics, we often have a designated base point, which is the bottom element, because we're typically dealing with an order structure and it's the least element. Okay, but the strict maps are what are the ones that preserve the base point. So I'll write it like this with Lolly. That's sometimes used as this is the part that I'm stealing from kind of denotational semantics notation. And what is that? So the strict maps from X to Y, another notation for that comes up is people will write this, and they'll write in denotational semantics, they'll write that, but unless I went through and changed all of my conventions so that the base point was always designated by bottom, then that wouldn't be a good notation. So, but you could use that. Okay, and what is that? Well, that's just the sum of all things. And now here's where this damn awkwardness comes in, okay? Because I have to have some way of referring to, really what I mean is x together with x naught, arrow, y together with y naught. Okay, so the cheating thing is, this is cheating, okay? I really mean the underlying type of the pointed type x and the underlying type. It's just one of those things that doesn't really work out. And then I have to cheat again and say f of x0 equals y0. Of course, I don't have to. I could really say x together with x naught, arrow y together with y naught, and then everything would make sense. But you're supposed to understand what this means. So we'll just write it like that. Okay, so we could do that. So it's the strict maps. It's the base point preserving maps. So in denotational semantics, that comes up a lot when dealing with like call by value kind of situations. That happens, and people are interested in the subcategory of strict maps that send divergent things here to divergent things here. So it reflects that aspect of call by value.
So this is only pointed up to homotopy, and we regard these things as different?
Yeah, so that's a very nice point. Yes, it's true. Because in the denotational semantics, thank you, you're working with structured sets or ordered sets, and so then the issue is there's no issue. Okay, but here, thank you, that's a very good point, right? So this is, it's again that situation. You can say up to homotopy. It's just that the whole point of homotopy type theory is that I don't have to say up to homotopy all the time. If I was going to say up to homotopy all the time, I would almost not bother with the hot part, because so the point is, in homotopy type theory, that is equality. So in a certain sense, if you know what I mean, it never makes sense to say anything other than they're equal. But that has the meaning, of course, as we've discussed at length, of up to higher homotopy, meaning that there's a path that witnesses the fact. So strictly speaking, you know, we have a base point on this type over here. F can sort of land over here, and then all you're worried about is that there's a path between them, you know. So yes, that's true.
But we regard two maps as different if we choose different paths?
Yes,
we regard two pointed maps.
Oh, that's a very good point. And now, because it is a proof-relevant environment, right? It could be, right, that a map on the underlying types is pointed in different ways. Okay, that's what you're getting at. That's true, which means the space of this thing, in principle, has a lot more structure. Now, of course, if we were working with sets, then this type is a prop, and then none of that is relevant. Okay, so in denotational semantics, right, because it's automatically true. If you don't have any choice about it. Okay, there's only one way for them to be equal, is what I mean, and so you wouldn't have that problem. Well, up to higher homotopy again, right? But in some sense, the issue doesn't ever come up if those things are props, because you just say, well, this is a prop. I mean, if this is a prop, which means those things are sets. So in denotational semantics, typically, as I say, we work with preorders or structured sets, order structured sets, and then one thinks of this as landing exactly on y naught, because there isn't, I mean, that edge has to be reflexivity, so well, up to higher homotopy. But in sets, it's not, in a plain ordinary set, that we don't deal with that, so we just write it as y naught. So yeah, that sometimes that can be confusing, and it can be important. There's recently been a discussion on the mailing list involved, for the people who are involved in the book, if you guys are on it, about saying something about things like this a little bit more explicitly. Okay, so that's the notion of pointed space. So the thing that I want to consider here is the following proposition, which will be familiar modulo the notation, which says that the maps from the suspension of A, the strict maps, for pointed types, so this is for pointed types. Okay, the strict maps from the suspension of A into B are equivalent to the maps from A into the loop space of B. This really means the loop space based at the base point. Okay, that's what we have to do here. So that's the the general setup. So let me just say a couple of things about that before I go further. Okay, so I have that here. Okay, so we did that. All right, so that's the setup. So so if you look at sort of, you can look at susp2, for example, and so that's going to be 2 into the loop space. It's going to pick out 2 loops, you could say, okay, inside of B. That's what is going to happen here. So this is a general thing. So in other words, these 2 guys work together. You can see it looks like a kind of an adjoint situation, right? That's what is being described here, and I'm writing it in terms of an equivalence. Okay, so we have to go back and forth. So let's see how we go back and forth. So given F, which goes from the suspension of A and it's strict to B, I want to define, I'm going to send it somewhere. I'm going to define G, which is where F is going to send it, which goes from A to the loop space of B. Okay? And as follows. So I want to do this. So what am I going to do? So I have a map from the suspension, okay, and I want to send it into the loop space. So what do? I take my argument A, and now I want to get a loop at A. So what have I got around? Oh, so I need 2 things. I'm not given merely, and this is exactly Spencer's point, I'm not merely given that let's write it in, we can write it in different ways. So let me write this down. It's a notational thing. It's the a little bit clumsiness of the notation. So what is F? So F is really a pair, okay, consisting of, let me call it F0 and P0, okay, like that, okay, where F goes on the underlying type. So this is the notational thing that's awkward. The underlying types, so F goes from susp A to B, that is the underlying types involved, and this is a proof that F preserves the base point. So we can write, F is just the raw map, is the map, and then we know we have a proof, and that's what's important, that F0 of, now what is the base point of the suspension? Well, that's north. So this to north is equal to whatever the base point of B is, because that we don't know, that's up in the air. Okay, that's up for grabs. So that's what I really have. So therefore, when I define G, that's the data I have. So I have lambda A is in here, and so I want to get a loop out of this thing. So what I can do is I can make a loop in the suspension in more or less the standard way by concatenating a meridian with its inverse. Okay, so the meridian at A0, which is the only thing I have around that I know about A for sure. All I know about A for sure is it's got a base point A0. Okay, so I make a loop that, so to say, passes through A0 using the picture that I've since erased. Okay, then we take the action of F on that guy. Okay, so this is going from this thing is going from north to north, right? If you think about it. So this is going from north to north. App F, what does that do? That gives us from F of north to F of north. We don't have any dependency to worry about here, so I don't need to worry about the path over. Okay, so that goes from there to there in B, because F takes us into B, so we have that. Okay, and now what I need, what is it that I need? Oh, I need a loop space in B here. Okay, something in the loop space of B, which means a proof that B0 is equal to B0. Okay, that's what I need. So that's where I get this. So where I use that. So I take P0 inverse and then concatenate with P0. And if I did that right, that's the calculation.
Does that not just give you a record?
Did I make a mistake?
Does that not just give you a record?
Is one of my...
Because you've got a path from north to south, and then you just concatenate.
Well, why don't I just send that to REFL?
Well, it looks like it gives you something which is definitely...
Oh, is it equal to REFL? Maybe so, because this is going to be equal to REFL. That's a good point, yes. So this is equal to REFL, because this is true. Yes, it's true what he says. It's true. What?
Your first A0 should be an A.
My first A0 should be A, that's why. Okay, good. I was trying to, while I was speaking that out, I'm thinking, why does REFL work? So, so yes, he's absolutely right, and thank you very much. Yes, I made a mistake there. Okay, yes, so that's supposed to be A. So then it's not. I was just about to say everything would cancel, and then I would have to say, well, why didn't I write REFL? But that's why. Yeah, I have it in my notes correctly. Okay, all right, so good. So now if you work it out, so I need to provide a Q, okay? So I need a proof, so I need Q, which says that G is base point preserving because, oh yeah, I'm sorry, this was supposed to say base point preserving over here. Did I mistakenly not write that down somewhere else? Yes, we want to write it here. This is base point preserving. Okay, so so now what I want to do is I want to have a Q. All right, so what I need is, which is a proof that G of A naught. All right, so G was going from A to the loop space, so I want that to be REFL of B naught because that's the designated base point of the loop space. Okay, so if you work that out, that's definitionally equal to P inverse app F, right, of, okay, now it's meridian. Now, you see, that's why as soon as Clive said that, I was thinking, yeah, it is true, it comes out to REFL, and then that's why, because of the next line, it comes out to REFL. That's why I thought that. Okay. Now it really is a REFL situation. And you just crank that out, and that's equal to REFL of B naught, which is good. We wanted that, so we're good with that. That was why. Okay, good. That was a very simple thing, but you can see how that goes. And now we can go the other way as well, flipping on the other side. Okay, so if we're given G from A as a pointed map into the loop space, and it's really neat, this is really going to be a pair, okay, which is G naught and Q naught. Just reminding you, which is the proof. So that was called, this is P naught over here, by the way. Yeah, I just carried that down wrong. Okay, so which is G naught and Q naught. In other words, a proof that it's base point preserving in the underlying map. So we'll write it like that. So now we want to define, what do we want to do? F, which goes from the suspension of A. I have to admit, it looks nicer when it says sigma somehow, you know, but anyway. So we want suspension of A to B. Okay, as follows. Okay, so what do I want to do? I want to take something from the suspension of A. Well, if I want to take, so kind of the reason I did this example was it's an illustration of the defining by recursion on suspension of A. So what I want to do is, what do I do with, so let me write it out like this. So F of N is going to be definitionally equal to B naught, because, well, okay, if you want to make me do this, if you want to really make me do this right, I'm defining F naught and P naught here. And then it's really F naught of N is B naught, okay, if we want to be meticulous about that. I told you it's something a little not smooth about those notations. Okay, and so we want to do, what does F naught of S do? So that is also going to go to B naught. This is basically, you could say, is forced. Well, it's not forced, but it's the obvious thing to do. It's supposed to be base point preserving, so you just make it base point preserving. And then you look at what app is, I have to figure out. And what I'm going to do here is, I'm doing the same trick I do when I write the elim forms. I'm going to, I don't mean this, so this should really be, you could write it like this perhaps. There has to be a witness to the fact that, okay, this is equal to or homotopic to G of A, okay? That's, or G, I should write G naught, I suppose. So G naught of A, okay, and that's the F in question, okay? And so do you see what I mean? Like when I wrote the recursors, I always end up at the 0 cells. These are definitional, that's no problem. At the 1 cells, I end up saying, well, you know, what I really mean is there exists an element which witnesses that. So I'll write that as like colon equals like that, and that's not too bad, I suppose. As I go along, I try to work out notational conventions that are nicer at the board, because I don't think any of us know what the best ones are yet. Okay, so we do that, and that's the definition. And then there's a big monster diagram. So I'm going to cop out here and say, see the text for the proof that these are of quasi-inverse properties. There's a big diagram chase to make that work out. But I just sort of what I wanted to say is that, you know, we're going back to. So the thing to be understood here is that we get more and more comfortable with it and we feel less doubt, but in a sense, you know, we're doing a new way of doing some of these arguments in homotopy theory. So it's very reasonable to suspect that definitions that look good aren't really right in some sense, okay? That they seem plausible, but they aren't the right ones, okay? So how do you say that they're the right ones? Well, you show that they all fit together in the expected way. I'm not sure if I know any other way to do that. Well, you can exhibit models as well and show that it works, but just because it works in a model, it might be, for example, the thing you specified is too weak, and it's okay to interpret it into some richer structure where everything is nice, but possibly you left something out, okay? Right, that's the general idea of axiomatics, right? So some of your axiomatics might be a little too weak. So if everything, at least on its own terms of its axiomatics, fits together properly, then that's an internal coherence that says everything is more or less what it should be. Okay, and the models don't help us. The models help us doing something that's flat out wrong. They don't really help us do enough to be right. That's what I'm trying to say. Okay, it's the same. It's a standard thing, and so the idea would be to make sure we've done enough to be right. Okay, so since things like higher inductive definitions are pretty much a new technology, it's conceivable that they're not really right yet, okay? And so all I'm saying is, as far as we know, they work pretty well. And someday we might decide that there are other axioms that need to be considered. So there we don't know, you know, that could happen. Okay, so now there's something that comes up quite a lot that I wanted to spend a little bit about, and it's kind of nice. I'm going to do an abbreviated version of this. Here, let me check my time. I'm okay. Which is looking at push-outs, which are generally used for various kind of amalgamation properties, and they're related to quotients, so I'm going to say something about quotients. So to warm up, again, I generally try not to assume too much background knowledge, so I'll give a rough account of what push-outs are, and then talk about how you do them with higher inductive types. The punchline is, the way you do them with higher inductive types is you just do them, okay? It's completely straightforward. But it's a very useful thing because it turns out the suspension itself can be thought of as a particular push-out, and there are many other push-outs. And so it's, that are of interest. And so it's kind of peeling back the layers. Okay, so just in case you're not familiar with this, so let's look at, you know, conventional, you know, set math setting. Okay, we're working in sets. So I'm not doing homotopy type theory now because there's some subtle issues that come up here. So let me just remind you. So what is the push out? Well, the way I think about it is dual to the pullback. So what is a pullback? A pullback is an equationally constrained subset in ordinary set level mathematics. It's an equationally constrained subset of a product. Okay? So if you want to form the pullback of two maps, you take the product of their domains, and then you constrain that product in such a way that the required commutativity conditions hold. Okay, so that's how you do it. It's a limit construction. So push out is dual to that. It's a equationally not constrained, but what is the opposite word I'm looking for? Equationally, I know quotiented I could say, but some equationally something. A set, you could look at it. So the idea is that the way you think about it is, think of these in ordinary, like, let's say we were doing a standard intro to category theory thing. Okay, so we have, which one, I want to get my letters right, otherwise I'm going to mess it up. Okay, so we have from this idea. So why does the idea of a push out come out? Well, the way I think about it anyway is we have sort of A over here and we have B over here. And in a certain sense, you could say we want to form the union of these two guys, except we don't want to form the union of these two guys. We want to glue them together in such a way that some designated piece of each one is identified with a designated piece of the other one. So that designated piece is sort of the image of C. So this is a copy of C in here, so it's the direct image. Like you look at the direct image, f of C here. I'll write it like that. And is it F? Yeah. Oh no, this one should have been G, right? Okay, is it? Yeah, G of C goes into A. All right, so then this is like F of C. In other words, you think of the parts that C, so C is being used, C is a picture, C is a diagram, and map is a picture of that diagram in B. Okay, so B has some other, who knows, some other structure, but a C-like thing is the direct image. There's a copy of C sitting inside here, and there's a copy of C sitting inside here by virtue of the fact that we have F and G given to us. So the data is given to us. It tells us how it fits in. And then what we want to do is we want to form an amalgamation, okay, which will be the push out, which is sometimes written like this, but it's a little ambiguous because you really do have to know the reason why C fits into A and C fits into B. So it's not like the nicest notation. But if this were like some inclusion, if we're working in sets, we could have an inclusion, then it would like make more sense. So it says, you know, keep these two guys disjoint, take the disjoint union of A and B, okay, and then identify F of C with G of C so that there's only one copy there. So we'll have over here up to bijection, you know, you have to like allow for that. Basically, let's write it as equals just to cheat a little bit. So F of C and G of C I called it. Well, those are going to be the same. And we're going to identify them insofar as their images are like that, and this is going to be their big thing. Okay, like that. So in particular, if you don't identify anything here, then you're forming the coproduct, the disjoint union of those two sets, okay? So it's a disjoint union in which designated pieces are glued together because you want to. So in denotational semantics, here's where it comes up. In denotational semantics, the way it comes up is sometimes people draw this picture. I have a type like that, and I have a designated base point here. I have it, a lot of times people write it like this. They let it hang outside. It's really part of the space, but I do it like that. So that's my A, and then this is hanging out here. And what I want to do is I want to form the disjoint union, but I want to do it in an eager sense, okay? So in other words, if I form the disjoint union, right, then what I will get is a space that has the in-left copy of the A stuff, the in-right copy, but then because this is really inside it, you'll also have an in-left of bottom, and you'll also have an in-right of bottom, okay, as you form the disjoint union. And then people want to smash these together, okay, to make the coalesce thing, so that these are both just bottom, okay? So these get identified and are my notation is slightly failing me here, but these are the designated single bottom for both of them, okay? So that's a coalesced sum, I think it's called in denotational semantics. You coalesce the bottom elements after disjointly forming the other elements. So when you're working with ordinary sets, you can hack about like that. You can just, kludge around and just say, oh, there's an element in here and we'll make it over here and we'll do some hacky thing, and you just do that hacky thing, okay? But that's because you're working in sets and you can get away with it. But really, there's a structure here. It's not just like hacking around with the points and doing something like that, just like making some mess. There's a general construction here. And the construction and the notation, as I mentioned, is, so first of all, we give a universal characterization, right? We say, okay, and it's notated. It's the most common notation that I know about is you write that as you look at it like that, okay. And so it's saying it's a universal condition for every one of these pairs F and G. There exists maps. I'm not sure if there's a standard convention for those or not. I'll call them G prime or F prime, okay. Well, there exists a set like here, such that the diagram commutes. That is, F composed with G prime is G with F prime. That would be the idea, okay? And it's the least, so to speak, it's the least such thing, meaning that if you gave me any other, okay, thing that masquerades as a push-out, okay, then there would be a unique map to it, okay? That's the idea. So if you gave me some other pair of maps going to D, such that, because of my boring notational conventions, let's call those double prime. If you gave me any other such thing, then there's a unique map that goes like that. Okay, so you're saying that, so this I'll write bang, that's unique. Okay, so what you're saying is, it's the tightest thing that contains A and B, loosely speaking, but is identified by F and G. You need the F and G, but it's identified with respect to C. The C part is glued together. Okay? All right, so you see that? Okay, so that's the idea. So all this is big, like it's so trivial when you write down Toby type theory, but I guess I wanted to make sure that everybody knew. So the question is, in set theory, I want you to tell me, I want you guys who don't already know all this stuff backward and forward and better than I do probably, but to tell me what that set should be. So if I'm just doing ordinary Blackboard math, and we've never mentioned homotopy ever, so you would, I'm going to claim to you that any such scenario, all the push-outs you want exist in this setting, because I have great freedom to just plop down sets according to what suits my purposes, and plop down maps according to what suits my purposes, because there are no constraints. The maps don't have to be continuous or anything nice at all. They don't have to be differentiable or anything. They don't have to have any properties whatsoever. So you get to just write down whatever you want, and therefore lots of constructions tend to exist because you can always hack them up, okay, when you're working with no constraints. So, all right, so that's my way of thinking about it. So what would I write, not non-experts, what would I write down here? What should this thing be? Or is everybody an expert and you're sitting there drumming your fingers? Okay, that could be. I haven't been assuming that. Okay, so what should it be? There must be at least one of you who don't, like, have McLean under your pillow.
Do A and B outside of the image of F and G have to be disjoint?
It's hard for me to hear you.
Do A and B in the disjoint unit?
Yeah.
They have to be disjoint outside of the image of F and G.
And then the second part was?
Do they have to be disjoint outside of the image of F and G?
Yeah, right, they have to be disjoint. So the way we can do this, so one way to construct it is, you assume that you already know how to form the disjoint union of two sets. Let's say it's like we do, we in left and in right, or something like that. So we make sure we get them both out of the way, because we don't know yet which things have to be, we're not identifying anything yet, okay? So we say this, and then what do? Well, we mod out by some relation. And the important thing here is that in the conventional setting, these are sets and this is a mirror relation. There's no proof relevance going on. That's going to be important, because we're going to see something that happens when we worry about the proof relevance. So you do that, where R, usually we'll say it's the least equivalence relation containing, and now I need to have some conditions that R has to satisfy. So what is the condition that R has to satisfy to do the gluing? Well, it has to be, you relate, well, I need a for all here. So for every C in C, because you see, and if we're working in ordinary set kind of stuff, I can look at all of the points of C. There's no inhibition to doing that. The things are given by their elements. So I do that, and then what do I want to do? Well, I want to make sure that the diagram commutes. That's all. I want to take the least thing that makes the diagram commute. So I'm going to take the disjoint union and then glue it together in the most parsimonious way possible. And what is the most parsimonious way possible? Well, I want two things to be related. I want, because if you look at it, I want to say, if I'm using in left as my notation for the inclusions or whatever that I'm doing here, then you look at in left f of C has to be equated with in right of G of C. Okay? That's what we do. So it's just like my picture with bottoms. So with the bottoms and all that, then I have a base point that I'm preserving, and the maps preserve the base point. And I want to make sure that, well, first of all, I just don't give a damn about base points, and I form the sum I couldn't care less about base points. And I form the sum. I now have a non-pointed type, so I have to figure out what the point is. So of course, there are different ways to do that. I could adjoin a point that I feel like, okay, that's possible. But another thing for me to do is just say, oh, but according to the picture I was saying before, I can coalesce the base points of A and B under their image. So in that case, the F and the G are quite trivial. It's just the inclusion of the bottom. So we'll end up saying in left of bottom is equal to in right of bottom, which is what I said to you before. But more generally, whatever C is, that's like the index set or the picture, the diagram. And the F's and the G's tell you how to draw the picture in A and in B respectively. And then you want to make sure that with respect to the picture, they're all the same. Okay, so that's like what you do. And then you can prove, and I won't do this here, you can just prove for yourself that that really is a push out. So as usual, you know, the whole, in some sense, the whole idea, not the whole idea, but a big idea in category theory is abstraction, where you say, I tell you clearly what something is without committing or demanding that it actually exists. I just say a push-out is a thing that has this great property, and it's super good because it's unique up to something. There's usual some up to, but basically it's the unique thing that does something useful, and then you separately say, and there is one too, at least in particular settings. So that's a nice methodology. So that's what we're doing here. So that's what a push-out would be. In sets, they always exist, because everything I did here is something you can write down from the axioms of set theory and that you've done a million times. Okay, so this broaches two subjects for me. This broaches the higher inductive definition of the push-out, and it also broaches the subject of quotients. So that's why it's useful. Okay, so how do we define this as higher inductive type? Okay, so first of all, that's not such a good idea, okay? I should really call this the push-outs of pair, let's write it like this. To A, I called that F, didn't I? And G. Did I? Oh, God damn it. Yeah, of course I did it wrong. No, yeah, of course I did it wrong. Yes.
But here you did it this way, so maybe you should.
Right.
Oh, did I do it wrong? What did I do?
So here you have F going to A, and there you should probably do it earlier.
So this should it be the other way around?
But
Yeah.
maybe it's better to change that one, as it kind of makes more sense.
All right, since I seem to prefer the other way, regardless of what I wrote in my notes, let me do that. Okay, so now let me mess it up. What can I do? I'm not capable of getting all those things right, it seems. Okay, so, all right, so what I really need, so it's not very good notation to write that, because that's just the object part. But it's a push-out is a structure. It's not like, yeah, so I care about these maps as much as I care about that. Okay, so, and you should ask yourself, what are the F prime and the G prime here? I really should have specified those. What are F prime and G prime? So you can do that. Okay, so we do this. So how do we do it as a head? Well, lo and behold, this is the most trivial thing you could ever imagine. What you do is you have a family of 0 cells, one for each A. So I'll give this, I'm going to give the target a name, but the point is that in the third line I need to know F and G. That's what I was getting at. Okay, so I form my own version of disjoint union. If you're going to have higher inductive types, there's no point in having disjoint unions because, as a primitive notion, because it's a special case of a push out, actually, as long as you have the empty type, so that you're identifying nothing. Or it's a special case of a higher inductive type, okay? So I have this, so this is the 0 cell part, okay? And then I need a 1 cell. And what is the 1 cell? Well, as I said, higher inductive types are equationally constrained inductive types, are they not? But we're in a proof relevant environment, so we have this notion of what's called the glue, call it something, I don't know, which says for every C and C, that should look familiar. What do I want to do? I want to identify, so now I'll use this notation. So I want to identify in this space, or this type, what do I want to identify? Okay, now maybe I should get it right. It's the same thing I just said a moment ago, which was the reason why I said it. Okay, G of C, and you write it like that. Okay, and that's your definition. So it's a dawdle. I mean, if you have in your hand the notion of an equationally defined inductive type, and then I say, give me this particular equationally defined inductive type. What makes it inductive? I'm using inductive to mean it has this universal property that it's the least thing of a certain character where the character is characterized equationally. Okay, so those are colimits. Okay, so this is really an instance of a colimit, and you can talk about, I'm not going to do it here, you can talk about the idea of a cone. So this is an example of a cone, or cocone maybe, I don't know, I never get confused about that. Like that, and you want to have, which is the cone and that's a span, and this is the cone, I guess, yes, the cone over the span, yes. And then this is the universal cocone, okay, that is the best possible thing, because you're supposed to think of it as kind of pointing up. That's the F prime and G prime part, which is the universal amongst those, okay? So this is a cone, okay? That's the way you're supposed to think about that. And so, so you can do all this at that level too, because colimit is a short way to say equationally defined free construction like this, equationally thing. So that's what we're doing. Okay, so that's all colimits are anyway. And then dually you can talk about limits, which are they don't need the quotienting part, so they don't need a higher inductive, but they do need a subsetting part. They need some way of talking about imposing constraints, and typically sigmas are the way to do that. You have to worry about the homotopy type of what you're doing, and we'll get to that in a minute, but approximately that's the story about how that goes, okay? So what is going to be like the induction principle or the recursion principle for this? So this is what puzzles me. So possibly what I'm going to say is wrong, but I was writing my notes last night and I thought, I don't know, this is what I came up with, and it's not exactly what seems to be in the book, so I thought, all right, so maybe this is fishy. But what seemed to make sense to me is, for the recursion principle, is I have a way of computing, I called it a D, okay, so, because I'm thinking of this as my D. So the general pattern is, I'm going to say, well, give me an L and an R. Oh, God, let's hope this was the L. All right, give me an L and an R. Okay, well, for such a scenario, give me an L and an R by virtue of the colimit, the push out being given by the higher inductive type, the mediating map, which is guaranteed by it being this free construction or this colimit, is going to be my recursor. Okay, so that's what I was thinking. So this is what I wrote. It may be exactly, I don't know, it was after midnight. I drove 8 hours and then I prepared my notes. So maybe I screwed this up. But this is what seemed to make sense to me. Okay, so you give me an L and an R that look like that, okay? But now you must make sure that you respect the gluing. So for any U, I called it for any U and C, you give me, let's call it a Q, okay? Which says that F of U for X in L, so the F is the one that goes to the A, yeah, so we're good, okay? Is equal to G of u for x in R. Okay, you could say L of f of u if you want, R of f of u. So if we say that, then someone, Spencer or somebody, will tell me why I'm wrong. But it looked like this is what we should get. We should get a recursor. That's the unique map guaranteed by that. Okay, of x dot L, y dot R, and u dot Q should be, let's see, I didn't do the dependent version. So we just do this, and then I would expect that rec blah, 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 applied to the in left of A should be definitionally, because it usually is, A for XL. And when the same thing is applied to the in right of A, I'm thinking this should be B for X or Y or something, Y, R. And then I'm thinking that the app of the rec over here, when applied to the glue on some element C, should be at least homotopic to C for UQ. Okay, so that's what I thought. Okay, but it doesn't exactly look like that in the book. So it could be I was tired and that is what's in the, it's not literally what's in the book, but it might be equivalent to it. And I didn't check whether it was equivalent or not. Oh, I'm 1150. Okay, and I didn't check whether it's 1150. Well, I didn't do that either, but I didn't check. I didn't check whether this is completely equivalent to the thing that's in the book. My head's running ahead. And now you can check, by the way. So you give a little exercise that's worth working out. Is you can check that the suspension of A is. This is a little bit cheating to write this notation, but it can be written like this. But it's not really cheating, because what I'm really saying is take A. There's a unique map from A to 1. There's a unique map from A to 1, and form their push-out, which is written like that. 1. So here, this is arguably a perfectly reasonable notation. Okay, because the bangs are, there's only one. So there's, so we can maybe agree that that's a good notation in that case. Otherwise, you have to do something clumsy looking to write down what you mean. So you have to write push out of this diagram. I don't know a nicer way. So you can show that the suspension is the amalgamated sum, you might say, or the push out of 1 and 1 with respect to A. So the with respect to A here is just the A many meridians. That's what's being said here. Because otherwise you think, what does it mean to glue together the unit type with respect to A, okay? Because the damn picture of A, however complicated A is rather degenerate by the time it gets to 1. Okay, so it's really not, yeah. So you wonder, what does it mean to identify that? Well, what it means is that it's the A many meridians, okay? There's going to be A many equations, okay? So this guy could be called north, this composite could be called north, and this composite could be called south, because it's at the bottom of the diagram. And then that gives you a hint now, because the equations that are implied are going to be equations between south and north, and there's going to be A many of them, okay? So voila. Okay, so now I gave you the answer. So that's how that works. Okay. All right. I thought I was going to get further, so I'll pick this up next time. There's a few other things about higher inductives I want to mention. Quotients. I want to revisit truncation, and then I hope to show one proof about the fundamental group of the sphere, so of the circle. So I'll show you that next time.